We're now going to look at the ways that a person's experiences and expectations influence perceptions of objects. In other words, we're going to examine the contribution of theory-driven processing. This is the same, remember, as top-down processing, which is the term used in the textbook by Revlin. So theory-driven and top-down are the same. Think of it as top-down is referring to like your head, your brain, so sort of your expectations in that sense, which is the same as theory-driven processing. So look at this picture. At first, you probably see the big picture, or what are called global features, of mountains and the stream. Look more closely, though, and you may notice that the mountains, rocks, and meadows contain images of animals. Once you see one, noticing the others gets easier. The data is the same as what you originally were looking at, but the expectation that there will be animal images helps you perceive those images. Another example is found in the perception of speech. The context, as we already know, is very important for speech perception. So here's this example. I saw a man on a hill with a telescope. How you interpret that depends on the context. Did you look through a telescope to see him, or did you look across at a man on a hill and he happened to be using a telescope? Pure word deafness is the ability to hear words, but only as sounds, not as language. This suggests that perception of words goes beyond just hearing the words, which is the data-driven processing for speech perception. So the data alone, the sound of speech, is not enough for people to be able to understand speech. Here's another example. Wouldn't you think that it's easier to perceive a single letter than a whole word? However, the opposite is true. In the word-superiority effect, the observer sees either a word, such as W-O-R-D, word, or a single letter on the screen. Then the word or letter is covered up, it's masked, with X's and O's. That way you only see the word or the letter really, really briefly. It just makes the task a little bit, more difficult, more challenging. Finally, the observer must decide whether it was a letter K or a letter D that was shown in the initial stimulus. The surprising result is that observers are better, people do better at detecting the existence of the letter D if it's in a whole word, if it's in a real word, than when the letter D was presented all by itself. We perceive letters better when they are within the context of a word, and it really shows the impact of top-down processing on reading. Now take a moment and read the text on this slide. So reading is a combination of data-driven and theory-driven processing. The data is the visual stimulus. In this case, the visual stimulus includes the features that form the shapes of letters. Because of our familiarity with letters, we can recognize them. From there, we use our familiarity with the language to put the letters together into meaningful words. Now, take a moment and try and read this. Feel free to pause the video so you can read it. Okay, so now that you've read it, first off, it's not true that only 55 out of 100 people can read this, and it's not true that this was from a study done at Cambridge. But we can read it for the most part. Why? How? What is the data, and what is the theory? How can we read it even when the data is so poor? If you read any of that, it was because your expectations for what those words could be or should be, that really helped you out. Another type of object perception that relies on theory-driven processing is face perception. As humans, we generally have a very good ability to read faces, even as infants. In this picture, you can see how babies, only 2 to 3 weeks old, can imitate an adult face. That's amazing. We can think of faces as a type of prototype. So we've seen prototypes already. We can think of them as a type of prototype. Faces are highly varied, in other words, they're all really different. And except in rare circumstances, no two are alike, yet they share significant similarities. They always contain the same set of parts: eyes, nose, mouth. the parts always appear in the same basic configuration. And so from that, we sort of create a prototype of a face. Look first at the 4 pictures on the left. So these are pictures of the former British Prime Minister, Margaret Thatcher. Focus first on the top 2. Do they look normal? They are not normal. The bottom set has the same pictures, but now they are right side up. I bet the one on the left looks very weird. Her eyes and mouth are upside down, and it really stands out as strange when the picture is right side up, but not so much when it's upside down. Now look at the picture of the boy on the right. I'm going to spin his picture around. Just keep looking at it. And oh, look at the one on the left as it starts to go right side up. The typical person will notice that the face on the right is sort of weird after the figure has been rotated about 72 degrees. So we're pretty standard in this. Here are some more examples. I bet that some of these look off, even though they are upside down. And here they are right side up. Apparently a big smile makes it easier to notice that the upside down face is wrong. When we look at right side up faces, we process these in a Gestalt-like holistic way. We use the spatial relations among the face parts to construct a holistic view of an individual's face. When we look at upside down faces, holistic face processing is disrupted. We can't do it anymore. And so we switch to noticing the individual facial features instead of their spatial relations to each other. In other words, we lose our special face processing ability and start seeing faces like other objects when they are upside down. And while we're on the topic of face perception, you might wonder if there's any evidence that we process faces of people our own race better than the faces of people from other races. It turns out that we do. This is called the cross-race effect. This effect is not just the result of having more experience with faces of your own race either. So here's how this was studied. The researchers created an ambiguous race face. So the face on the far left is missing its hair, and it's sort of ambiguous whether the individual be of a Latino background or ethnicity, or of a Black or African American ethnicity. When a Hispanic hairstyle is added to this ambiguous race face, that's the picture in the middle, the face is perceived as Latino or Hispanic. When a Black hairstyle is added to the ambiguous race face, that's the picture on the right, the face is perceived as Black. Hispanic students are more likely to recognize faces perceived as Hispanic than those perceived as Black. Because the faces are identical except for the hair, top-down or theory-driven categorization as the person being either the same or some other race must contribute to the decision. So our expectation of the person as being of a particular race seems to influence our ability to recognize and remember that face. In the brain, the fusiform gyrus is critical for face recognition, which shows that humans come adapted to look at and recognize faces. In this drawing, the orange area represents the fusiform gyrus. So it's at the bottom of the temporal lobe. Your textbook has information on how people with specific neurological problems, including prosopagnosia, schizophrenia, and autism, have difficulty with face recognition. So please take a look at your textbook, the Revlin textbook on cognition, for that information.